My name is Neha. I am a student of BSc Chemistry on the 5th semester and I am here for making a presentation video on topic spectroscopy and NMR. So let's get started. NMR stands for nuclear magnetic resonance. First of all, we will start from the principle of NMR. Let us consider a spinning nucleus in presence of external magnetic field H0. Now this external magnetic field tries to align the spinning nucleus in its direction. As the nucleus is spinning, it will not align in the direction of the magnetic field. Instead, it will start rotating in this form with a frequency omega known as precessional frequency, and this motion is named as precession. Now when this precessional frequency is equal to the frequency of the electromagnetic radiation to which the substance is irradiated, then the absorption takes place. At this point of time, the nuclei changes its state from lower energy to higher energy. At this point of time, the nucleus and the electromagnetic radiation are in resonance with each other, and hence the phenomena is known as NMR, that is nuclear magnetic resonance. Now we will study about the types of NMR spectrometers. Basically, these are of two types. One in which magnetic field is kept constant. First are in which magnetic field is kept constant and radio frequency is changed. The second type of NMR spectrometers are those in which magnetic field is changed and radio frequency is kept constant. These type of spectrometers are known as WNMR spectrometers, and this class of spectrometers is known as continuous wave, that is CWNMR spectrometers. Here we will particularly study about the magnetic resonance in protons, hence the name comes PMR. Now we will proceed further with the study of PMR signals. In PMR spectroscopy, solvents that are used are those which do not have protons, that is hydrogen atoms. For example, CdCl3. Now we will study about two types of protons, that is equivalent and non-equivalent. Equivalent protons are those which have same environment. On the other hand, non-equivalent are those which have different environments. In case of equivalent protons, only one signal, that is same signal, and in non-equivalent protons, they give different signals. Now we will discuss about the position of signals in PMR spectroscopy. In PMR spectrum, the position of signal varies with the phenomena known as shielding or de-shielding. In the process of shielding, when induced magnetic field opposes the applied magnetic field, opposes the applied magnetic field, then the actual field acting on the proton decreases, and hence more magnetic field will be required. Hence the spectrum, PMR spectrum, shifts upward, that is upfield. As in the case of de-shielding, the induced magnetic field reinforces the applied magnetic field, and in that case, the total felt magnetic field on the proton increases, hence the spectrum shifts downfield. Now the shift in the PMR signal due to shielding or de-shielding is termed as chemical shift. Most commonly used unit for chemical shift is parts per million, that is ppm. To do this, the chemical shift in hertz is multiplied by a factor of 10 raised to the power 6 and then divided by the oscillator frequency of the instrument. That is, if we represent this chemical shift with delta, then delta is equal to this frequency, oscillator frequency in hertz, delta nu into 10 raised to the power 6 upon the oscillator frequency in megahertz. Now we will talk about the factors affecting chemical shift. The number one factor is inductive effect. Number two is anisotropic effect. And number three is hydrogen bonding. In inductive effect, the proton shift is increases as the electronegativity of the atom attached to the carbon bearing hydrogen increases. This is due to the reason that minus I effect of the electronegative atom decreases the electron density around the proton, which causes de-shielding. Thus, higher the electronegativity, higher the de-shielding, and hence higher the value of delta. Now, in the second anisotropic effect, depends upon the orientation of the proton relative to the induced field, mainly due to anisotropic effect and partly due to sp2 hybridization. The olefinic and aromatic protons are much more de-shielded when sp3 hybridized.
एक
And lastly, in case of hydrogen bonding, as we know that hydrogen bonding decreases the electron density in OS bond, therefore the proton involved in hydrogen bonding gets deshielded and hence the value of delta increases. Now we will study about the splitting of signals. Now we will study about the splitting of signals due to spin-spin coupling.
एक
Now as we have discussed earlier that for one set of equivalent protons, only one PMR signal is observed. That is, the number of signals in a PMR spectrum is equal to the number of different types of protons present in the molecule. Now let us consider this phenomena by taking an example of CH3 CH2Br. By looking at this compound, it is seen that the compound will give two signals, one due to A type of protons and the second due to B type of protons. But this is not the case. Instead it shows 5 P's. This is due to the interaction of the A type of protons in the B type of protons and simultaneously vice versa. The splitting of PMR signals has been found to depend upon the environment of the absorbing proton with respect to the protons on the adjacent atom. Let us take an example of this group CH2CH. The actual magnetic field which a secondary proton feels at any particular moment is increased or decreased slightly by the spin orientation of the nearby tertiary proton. The field would be increased if the spin of the tertiary proton is found to be aligned with the field at that moment, and decreased if the spin of the tertiary proton is found to be aligned against the applied field. But it is reasonable to assume that at any given moment, but we know that the probability of alignment of the spin of tertiary atom, but we know that at any moment of time, the probability of alignment of the spin of tertiary proton with or against the applied field must be equal. That is, half the molecules of the secondary proton will feel an increased field and thus absorb downfield, and half will feel decreased field and hence will absorb upfield. Thus the absorption signal splits into two signals, that is 1:1, and hence forms the field. The multiplicity of the tertiary proton signal. It would be affected by the spin combinations of the two adjacent protons. Now there are four probable combinations of spin alignments for these two protons. One can be that both have upward spin, both have downward spin, and half of the protons have upward and half downward, and vice versa. relative intensities of three peaks in this triplet are 1:2:1. That is, the center peak will be almost double in intensity than the two outer peaks due to the combined probability of the two equivalent combinations. The spacing between the two peaks of the doublet is exactly same as the spacing between any two adjacent peaks of the triplet. This is because of the spin-spin coupling is reciprocal process and the coupled protons affect each other to the same extent. This spacing is termed as coupling constant. And its unit is Hertz. Here comes the concept of Pascal's triangle, which is used for predicting the relative intensities of the peaks in a multiplane. We write Pascal's triangle in the following way: 1:1, that is doublet. This was singlet, this is doublet. 1:2:1, this is triplet. 1:3:3:1, this is quartet. 1:4:6:4:1, this is quintet, and so on. Now we will study about the rules for splitting of proton signals. The first rule is that splitting of a proton signal is only caused by non-equivalent neighboring atoms, or we can say vicinal protons. Let us take an example of methionine dichloride, that is CH2CH2 chlorine atom attached on both carbon atoms. Now here it is observed that splitting of proton signal do not take place due to the presence of vicinal protons are equivalent to each other. Rule number 2 states that the splitting of one proton by another proton happens on the same carbon, that is geminal coupling, when the two geminal protons are non-equivalent. Let us take an example of isobutylene and 2-bromopropene, that is carbon-carbon double bond, methionine group on one carbon and two protons on another carbon. For 2-bromopropene, in the case of isobutylene, two vinyl protons are equivalent and hence no splitting takes place. Whereas 2-bromopropene, two vinyl protons are non-equivalent and therefore splitting is observed in this case. Third rule is that the number of peaks into which a given proton signal is split is equal to one more than the number of vicinal protons. That is, multiplicity of a proton signal is n plus 1. This statement is termed as n plus 1 rule. Now we will study about the applications of PMR spectroscopy. The first application is identification of substances. Like in the case of IR spectrum, PMR spectrum is also used as a fingerprint of the substance. If the PMR spectrum of a given sample is exactly equal to the known compound, then we can say that the given compound must be identical with the known compound. In this way, PMR spectroscopy can be used to establish the identity of substance. Second application is the determination of molecular structure. Second application is the determination of molecular structure. PMR spectra are often very complex, but this complexity can be used in determining the molecular structure since it makes the spectra characteristic. Furthermore, even the complex spectra can be made interpretable by using the techniques of repairer labeling and double resonance. The third application is identification of reaction product. Wherever in a reaction two or more products are theoretically possible, PMR spectroscopy has been used to identify the actual product. The fourth application is distinction between geometrical isomers. PMR spectroscopy can be used to distinguish between cis and trans isomers. The fifth application of PMR spectroscopy is that it helps in the distinction between inter and intra-hydrogen bonding. Now we will discuss about the limitations of PMR spectroscopy. The first limitation is PMR spectra are recorded only on liquid samples. The second limitation is enantiomers cannot be distinguished using PMR spectroscopy. But recently this limitation is has been overcome by using chiral solvents. PMR spectra of some molecules, like for example, ethyl bromide CH3 CH2Br. The PMR spectrum of ethyl bromide shows two signals, one triplet and one quadruplet. As it is clearly seen that in ethyl bromide, two types of protons are present, A and B. The three protons of CH3 group are magnetically equivalent and hence produce one signal. Similarly, two CH2 protons are magnetically equivalent and thus produce another signal. Due to minus I effect of bromine, the electron density around CH2 proton decreases related to CH3 protons. Therefore, CH2 protons are deshielded related to CH3 protons. In other words, CH2 protons absorb at a lower field, that is delta 1.7, 3.4, then CH3 protons, which is delta 1.7. Integration reveals that the relative areas under these two signals are in the ratio 3:2, that is the number of protons. Further, due to the presence of two protons on the adjacent CH2 group, the signal due to methyl protons is split into triplet in the ratio 1:2:1 in accordance with n plus 1 rule. Similarly, signal due to CH2 protons is split into a 1:3:1 quadrat by the three equivalent CH3 protons. Also, it is found that the spacing of peaks, that is coupling constant J, within the three lines of the triplet and four lines of the quadrat is the same and is equals to 7 Hz. Now let us consider the second compound, which is N-propyl bromide, that is CH3 CH2 CH2Br. In this, it is clearly seen that there are three types of protons, A type, of B type and C. The PMR spectrum of N-propyl bromide shows three signals, one triplet, a sextet and one triplet. N-propyl bromide contains three types of protons marked as A, A, B and C. Their relative areas being 3:2:2. Due to minus I effect of the bromine atom on the C protons, de-shielding is most experienced, and hence these protons appear at the lowest field, that is delta 3.45. Since the minus I effect decreases with increase in distance, therefore B protons are less de-shielded than C protons, and hence lower value of delta, that is 1.95. The most shielded protons are A-type protons, which absorb the highest field and lowest value of delta, that is 1.1. The signal due to A protons is due to 3 equivalent CH3 protons. It is split into 1:2:1, triplet by 2 equivalent methylene protons of type B, with a J value of approximately 7 times. Similarly, the signal due to C protons at delta 3.45 refers to methylene protons of CH2Br. It is split into 1:2:1, triplet by the methylene protons, that is Hb, on C2 with J value approx 7 times. And the split of the Hb protons is 1:5:10:10:5:1.